All right, hello class. Here we are, lecture 20, continuing our discussion in criticality and phase transitions, focus largely on a real workhorse model for uncovering notions of universality and symmetry, the so-called Ising model. We've been interrogating it in lots of different details through the guises of different dimensionalities, trying to uncover basic truths about things that are as commonplace as liquid vapor transitions, but which are, as we've argued, analogous to the demagnetization of a magnet. So we have come to a point where we can convince ourselves that this model, albeit simple, has the essential physics to predict quantitatively accurate behavior of things like liquid vapor transitions, and that it is in the same universality class as liquid vapor transitions for molecular fluids. And we've also convinced ourselves that trying to study it is difficult. The existence of a phase transition necessitates correlations. Correlations require interactions. And using the tools that we've built up over this course to compute things like partition functions is really stifled. Those tools we've used throughout the course are stifled when it comes to trying to study interacting systems. So we need to develop some new toolkit. We've introduced one means of trying to approximate the partition function for the Ising model using so-called mean field theory. We're going to elaborate upon that theory again today, after we remind ourselves about some of the basic phenomenology of the Ising model. And we'll get to a point where we can identify exactly what we're missing using mean field theory and what we might be able to do in order to account for that lost information. So before we go down that specific road, let's remind ourselves of some basic aspects. So first, all of this discussion is within the context of the Ising model. The Ising model has an energy function, which is pretty simple. There is an interaction term with strength J that couples nearest neighbor spins, Si and Sj. That sum is restricted over nearest neighbors and denoted with that prime. So that term is what causes interactions between spins, what results in correlations between spins. And in addition to that exchange coupling, we could envision applying an external field with strength H, which might favor pointing the spins up if H is positive, or pointing the spins down if H is negative. That field is conjugate, as we might expect from thermodynamics, to the net magnetization, which is denoted M and computable by summing over all of the spins. So those are the two terms in our simple model. There is a bilinear nearest neighbor interaction term and an external field. In the absence of the external field, that energy function has up-down symmetry. It is left invariant if I take one configuration of the spin system and flip all of the spins at once. So that's a model. It's important to ask, how well does that model reproduce, say, what we would expect to see in a real magnet? So a real magnet, for example, if we were to measure its net magnetization, say per spin, so some magnetization density, as a function of, say, the temperature. Well, at low temperature, magnets exist, easy access magnets that point along one direction will have, at low temperature, some finite magnetization. So it might point up, or by symmetry, down. If I heat that magnet up below a special temperature, denoted Tc, that magnetization goes away. And the way in which it goes away will look something like this, where far away from the critical temperature, the details of that loss of magnetization may be complicated and may not itself be universal. But near Tc, independent of the magnet we're looking at, that magnetization goes away in a universal manner. If I look at the modulus of the magnetization as a function of temperature relative to the critical temperature, it goes away in a power law form with some critical exponent beta. And for magnets in 3 dimensions, or the Ising model, that critical exponent is 0.32, provided that Ising model exists in 3 dimensions, like most easy access magnets do. So again, while at very low temperature, the Ising model might not do a faithful job of predicting the dependence of the magnetization as a function of temperature. Near the critical temperature, it acts in a universal manner. It predicts a universality, which is that measured experimentally. Analogously, if I was going to measure the susceptibility, which for a magnetization transition is how the magnetic moment varies with applied field at fixed temperature. Well, at low temperature, I have to apply a pretty large field to change the magnetization. In fact, this is also already actually a little misleading. At 0 temperature, I have to apply an infinitely large field to get a change in the magnetization. But that susceptibility increases upon increasing temperature. You might remember that the susceptibility is proportional to the fluctuations in the magnetization. At 0 temperature, there are no fluctuations, so the susceptibility is 0. At very high temperature, there are fluctuations that are larger at low temperature. But it turns out as we approach that critical temperature, the susceptibility, or correspondingly the fluctuations, diverge, become infinitely large. They do so in a very universal manner as a power law of temperature relative to the critical temperature with an exponent, gamma, which, whether or not we're measuring real magnets or studying a 3-dimensional Ising model, yields the same universal behavior with a critical exponent in 3 dimensions of 1.2. So indeed, real magnets behave in this way, and this is essentially how the Ising model predicts the behavior to go. It might be that some of the details at very high temperature or very low temperature are not quantitatively predictable using the Ising model, but near the critical transition where those molecular details don't matter, we recover the expected universal properties. All right. So we've already alluded to, in words, the importance of dimensionality. Indeed, we have solved the Ising model exactly in one dimension. Using a transfer matrix technique. And while that's a nice calculation to do, in part because it, a reflection of the fact that it was analytically tractable is that in one dimension, there was no phase transition. If we were to look at the magnetization as a function of temperature in the one-dimensional Ising model, let's use a different color, at t is equal to 0, that's not quite right, I would have all spins up or all spins down. But immediately away from t equals to 0, I would have no net magnetization. Oh, that's really ugly. Let's try this again. Immediately at finite temperature, the average magnetization would go away and be 0 for all temperatures. So while there is a degenerate ground state where I can have all spins up or all spins down, at epsilon away from 0 temperature, there would be no symmetry breaking, there would be no finite temperature critical point with associated critical exponents. Indeed, if I was to look at how the magnetization was altered with an applied field at any finite temperature, I would see a smooth curve. I could smoothly go from all spins up to all spins down by applying large enough fields. And we rationalized this observation with Landau's argument of the non-existence of discrete symmetry breaking, up-down symmetry breaking in one dimension. An interesting historical note, the Ising model is so named because of Ising, who was a graduate student thinking about phase transitions, thinking about magnets. He wrote down his model, solved it in one dimension, found that there was it did not predict a phase transition, and essentially abandoned it and science as a whole. So he got his PhD having constructed the Ising model, which is now an incredibly important model in our field, but thought it was a total failure because it didn't predict a phase transition. He didn't understand at the time that 1D was special had he been able to solve it in 2 dimensions, which was done by Onsager quite a while later. He would have been much more happy with himself, I think. So indeed, while the one-dimensional Ising model does not predict a phase transition in a real tour de force of matrix algebra, Onsager solved the Ising model in 2D, demonstrating that in 2 dimensions, in the infinite limit, there was indeed a singularity to the free energy, a finite temperature critical point, so Tc, turns out to happen at twice J over Kb divided by some irrational number, 1 plus square root of 2, pretty close to 2.26 J over Kb. But associated with that transition in 2 dimensions are critical exponents, which are not those observed experimentally, at least for 3-dimensional magnets, as we alluded to or discussed last week. If you study 2-dimensional, macroscopically 2-dimensional systems in reality, like a lipid bilayer made of 2 lipids that can undergo a demixing transition, because demixing exists in the same universality class as magnetization. If you measure the critical exponents associated with a demixing transition, you find exactly those predicted by Onsager's exact solution. So an important point that we learned in the last couple lectures is that dimensionality is really important in the study of phase transitions. 1D is special in these sorts of transitions in that there are no transitions in 1D. We also noted another dimensionality, so-called four-dimensional Ising models, which start acting in a simple way. So we have discussed that higher than 3-dimensional systems, while not so conducive to experimental interrogation, can be studied numerically. And if, for example, one noted the critical exponents as a function of dimensionality, for 1, there's no transition. For 2, they are exactly those predicted by Onsager. For 3, we've discussed them a lot. For 4, 5, etc., the beta critical exponent takes on a very simple number. It's just a half. For 4 and higher dimensions, the gamma critical exponent is just 1 for 4 and higher dimensions. So the 3-dimensional Ising model, solvable numerically, yields exponents in agreement with experiment. We would say that 2 dimensions represents a lower critical dimension for the system, below which there are no transitions. And for dimensions higher than 3, the fact that all of the critical exponents remain unchanged for 4 dimensions and 5 dimensions is itself an interesting observation, and thus D greater than 3 or 4 dimensionality of 4 is often referred to in this context as the upper critical dimension. And so that's another observation that we'll try to understand in the next couple lectures. Okay, so that was all a bit of a review. I want to actually continue reviewing by means of redeveloping mean field theory as we've done previously. So mean field theory is an example of an approximate solution to the Ising model. And is one which is pretty reasonably physically motivated. So mean field theory is often considered as taking a lattice of spins, like that shown in 2 dimensions here, and imagining trying to replace all of the fluctuating spins with which a single tagged spin interacts. So let's imagine tagging this spin here, which interacts with its neighbors above and below, to the left and to its right. Those spins impose effectively a field which biases it in different directions. And rather than trying to consider the complete complexity of that fluctuating field, we replace that fluctuating environment with just its average behavior. So we go from a complicated interacting system to a single spin interacting with some mean field, and hence the name. And so that's the basic idea. The basic physical motivation is to replace a complicated interacting system with an effective single spin problem, which we know how to use. So that puts it right in the wheelhouse of the separable or factorable partition function calculations we've done all year. So that's the idea. Mathematically, this is straightforward. We say that the energy function is now some effective field multiplying each spin, where that effective field we can write down exactly from the original definition of the Ising model. It has a direct field component, a piece that would be there even in the lack of spin-spin interactions. But in addition, there's an interacting piece that depends on the exchange coupling and however many neighbors there are to the tagged spin we're considering. That's the fluctuating field because it depends explicitly on fluctuating variables Sj. So in the mean field approximation, we replace those fluctuating Sj's with their average value. So H effective goes to H plus J times the number of neighbors Z, and little m, which is just a stand-in for that average value of S. So now we've taken our interacting system and turned it into an approximate single spin problem. So the probability of seeing our tagged spin, Si, in some specific state is now just proportional to a Boltzmann factor e to the beta a number, H effective, times the value of that spin. independent of all the other spins. So if it is independent, its partition function is just given by an enumeration over its own internal states. So if we denote little q as the single spin partition function, it is given by a sum over the two values that Si can take, which are nothing but plus or minus 1, each of which weighted by this mean field energy function, which is an easy sum to do. It's going to have two terms, exponentials with opposite signs, a sum of exponentials with opposite signs in their arguments, which is one way of denoting the hyperbolic cosine of its argument, in this case, beta h plus beta jz m. Twice that is then the single spin partition function. From that single spin partition function, we can then ask questions about the average and fluctuation behavior of our single spin. So for example, we can compute the average magnetization of that tagged spin. By remembering that the average magnetization is given by the derivative of log the partition function with respect to its conjugate field, beta h, holding everything else like temperature fixed. When you take the derivative of twice hyperbolic cosine beta h plus a constant with respect to beta h, you get that m is equal to hyperbolic tangent, the argument of the hyperbolic cosine beta h beta jz m. And now we note that we have a bit of a predicament because m is now on both sides of this equation. So we've not actually solved for m. This is a transcendental equation. We then have to solve self-consistently to determine the value of m. So mean field theory then has kind of two pieces: the physically motivated effective energy function that a single tagged spin feels to make a non-interacting system that we can solve, and then a assertion that the averages we get out of that approximate solution are self-consistent, that the average we compute from that mean field system is the average that we put in. Namely, it's the average that is that tagged spin feels due to its neighbors, so that that tag spin is not special. It's just like all of the other spins. So its average value should be the same as the average value of its neighbors. We can dictate that by demanding in this equation self-consistency. That makes our life a little hard because that transcendental equation does not have a simple closed form solution in general. But near TC and along the line that h equals 0, we can get some insight through graphical solutions and Taylor series expansions. So near TC, and for H is equal to 0, we expect the value of the magnetization to be small, in which case the hyperbolic tangent of beta JZ M can be approximated to first order in M as beta JZM. Hyperbolic tangent is a strictly odd function, so that's good up to m to the third. Noting that initial slope for small m and that hyperbolic tangent of x goes to plus minus 1 as x goes to plus minus infinity, we have enough information to then understand that there are two classes of solution for this transcendental equation. Graphically, if we were to plot those two functions against m, so we have the line with slope 1, m is equal to m. We're trying to find solutions to the equation where hyperbolic tangent is equal to that line. So that would be the places for which the values of m for which those two functions intercept. So hyperbolic tangent at 0 is 0, so that's a trivial intersection point. For beta JZ greater than 1, the initial slope will be greater than the line m is equal to m. That it has to plateau means that there is an intersection at some point. And let's denote that point of intersection for beta JZ greater than 1 as plus or minus m naught. On the other hand, if beta JZ is less than 1, that slope will be less than the line m is equal to m. I will still plateau at plus or minus 1, but now there's only a single root at 0. So we've just understood rather simply through our graphical means that the number of solutions depends on this initial slope. If we imagine fixing the lattice, and thus fixing the coordination number, and fixing J, the Baire exchange interaction, then what we are able to do to tune and thus afford different numbers of solutions is beta, which is another way of saying the temperature. So again, for beta, JZ is greater than 1. So for a particular temperature where that condition is satisfied, we have 3 solutions, a trivial solution at 0 and 2 degenerate solutions at plus or minus m naught. For beta, JZ is less than 1, there's only 1 solution at m naught. Thus, there must be some value of beta for which that behavior changes between 1 solution and 3 solutions. That temperature is then identifiable as a critical temperature, as the point at which there is a symmetry breaking between 2 non-trivial values of the magnetization. That change is where beta j z is equal to 1, or beta j, or jz over kbt is equal to 1, or rearranging that Tc, where I generate spontaneous broken symmetry, in the mean field limit is equal to jz over kb. So that's a real success of mean field theory. We were actually able to predict the spontaneous symmetry breaking at finite temperature in the Ising model. So you've seen this before. What we haven't discussed is how well this actually works. So for a square lattice, where z is equal to twice the dimensionality, if I was to list different dimensions, their actual critical point or their mean field predicted critical point, so that's a table make. So for 1, 2, 3, or 4, say, so mean field theory predicts a critical temperature at d is equal to 1, so for a one-dimensional system, which is finite, and 2. That's a terrible prediction. That is infinitely wrong because there is no finite temperature critical point in 1D. So let's put this in units where J is equal to KB is equal to 1. In 2 dimensions, as we've discussed, Onsager told us that the critical temperature was 2.26. Mean field theory predicts 4. Not great. For 3 dimensions, one can numerically establish that the critical temperature happens about 4.5. Mean field theory predicts 6. That's getting a little bit better. In 4 dimensions, the critical temperature as determined numerically is 6.6. Mean field theory is predicting 8. So it actually gets pretty better. That's actually better than 75%. So one should be optimistic at this point in our lives. So we could say that this is actually pretty good, pretty good at high dimensions. What about other properties? Can we predict other things within mean field theory for the Ising model and compare them? Can we get critical exponents? We've alluded to this already. Can MFT, mean field theory, predict critical exponents? Sure enough, so near TC, we know that M is close to 0, along H is equal to 0. If we just go to a slightly higher order expansion, so note that hyperbolic tangent of x is x to first order and minus x cubed divided by 3 to third order. That would mean that the solution to our self-consistent equation is given by M is equal to beta jz m minus beta jz cubed divided by 3 m to the third. That's a third order polynomial, solvable in general. Let's make our lives easier by noting that beta jz is the same as the mean field theory prediction of the critical temperature divided by the actual temperature. Indeed, the solutions will depend on temperature. This factor then is 1 by 3 Tc over T cubed. To first order in T relative to Tc, that is just 1 in this case. Well, let's not do that yet. Okay, so we can write everything down as Tc relative to T. So indeed, there's a solution for m is equal to 0. That's the trivial solution. There is, in addition, 2 roots for finite m, call it m naught, squared. So dividing through by m everywhere, assuming that m is equal to 0 root is not the one we're looking for, we can solve this equation and get 3 times Tc over T minus 1 divided by Tc over T cubed. To first order in T close to Tc, we can divide through by Tc everywhere. We'll have 3 times Tc minus T over Tc. So indeed, m naught as a function of T has 2 solutions, plus or minus 3 times T minus Tc minus T over Tc square root of, implying that for T less than Tc, we have a beta of 1/2. There's only one solution for T greater than Tc, and that's that m is equal to 0. So indeed, that prediction of the Ising model of our mean field theory looks very much like what we would have hoped for if we were to plot absolute value of m naught as a function of T. It would crash down into the m is equal to 0 line with some critical exponent. It's just the wrong critical exponent for anything other than a high-dimensional system. Okay, but it does predict a critical scaling, so that in and of itself is interesting. What about other critical exponents? So how about gamma, for example? So to remind you, gamma is the critical exponent that tells us how the magnetization varies with applied field at fixed temperature. This is evaluated near the critical temperature where H is equal to 0. And from universality, we expect that this depends as a power law of T relative to Tc with some critical exponent minus gamma. All right. So again, near TC, where M is close to 0, we can expand our transcendental equation, self-consistent equation. M is equal to first order H, so finite H, plus beta J Z M. The susceptibility is computable by from a derivative of that magnetization with respect to applied field. That we can take on the left and the right side, getting an equation chi, the susceptibility, is equal to 1 plus, reminding ourselves that Jz over Kb is Tc. That gives us Tc over T times chi. Or solving for chi, we get chi, the susceptibility, is equal to 1 minus Tc over T to the minus 1, which is indeed proportional to T minus Tc to the minus 1, yielding gamma at mean field is 1. So again, we find, if we're optimistic, that things are cool. We predict universal behavior, power law, functional forms for things like the susceptibility and the order parameter as a function of temperature. We can, having found spontaneous symmetry breaking at mean field theory, extract critical exponents like beta and gamma. The unfortunate thing is that those critical exponents are not those associated with a three-dimensional system. The cool and interesting thing is that they are those associated with the universal behavior of high-dimensional lattices. So to understand kind of what we're missing at low dimensions, we have to think about the approximation we've made at the outset. So first, again, to summarize, mean field theory seems to work at high D. It fails at low temperature. Extremely poorly for D equals 1, for example, where there is no transition. So what exactly are we missing? Okay, so let's go back to the physical assumption we made. We took our lattice of spins, say in 2 dimensions, might look like this. And we blurred out all of the spins save some tagged spin. And we said that that tagged spin feels only the typical behavior from its surroundings. So if we thought about now what we've missed, this tagged spin, through its interaction with its neighbor, is influenced to be up or down. We've got that to some extent in that mean field. The mean field influences the state of the tagged spin. In our original model, that tagged spin influences the state of its neighbors. So there's a back reaction, there's a correlation that can develop between adjacent spins that in our mean field theory, we don't really have. So the state of the neighbors is not directly influenced, the statistics of the state of the neighbors is not directly influenced by the state of the tagged spin. So the thing in which we're missing, what we've thrown out in doing a mean field theory, is the effect of correlations between spins. So in the original model, the state of any spin depends on its neighbors. That neighbor, the state of the neighbor depends on its neighbors, and so on. In our mean field theory, the state of the neighbors is independent of the tagged spin. So a name for those effects would be to denote them as correlations. The fact that the state of one spin influences the state of another spin is the statistical correlation of the value of the tag spin on the others. So how can we quantify that correlation? And why is it that it becomes important for high dimensions and not low dimensions? Why is it that it is important for determining critical behavior? Well, let's think about what happens exactly at the critical point. We've already discussed this. In fact, the existence of a divergence or a singularity in the partition function, a divergence in fluctuation quantities like the susceptibility, is manifest only because some correlation length, call it Kc, because it diverges at Tc. In fact, one could measure the correlation length and note that it diverges in a very particular way. It diverges as a power law of T relative to Tc with some other critical exponent nu, which in 3 dimensions turns out to be 0.63. We have discussed at the beginning that the divergence of this correlation length is really central to a phase transition. A way to remember exactly how that works is to remind ourselves that the susceptibility, something that diverges, is proportional to the fluctuations in the magnetization, where the magnetization is this extensive sum over spins. If I looked at the intensive quantity, the fluctuations of the magnetization per spin, from the definition of the magnetization as a sum over spins, I can work out that that fluctuation divided by n is 1 over n, a sum over I and j, the average of Si times Sj less the average of Si times the average of Sj. So this function here is something that, for the fluctuations in the magnetization to diverge, for the susceptibility to diverge, requires that all terms in that sum are finite. That requires that all of those averages are not independent. And so this term here itself is a direct reflection of the correlations between spins. If spins are uncorrelated, that term in the argument of the sum is identically 0, because I can average Si independently from Sj if they're independent random variables, and thus that first term would exactly cancel the second term. So in fact, it behooves us to identify Cij as a correlation function between spins I and j. If all spins are the same, I can sum over one of those spins, let's say I sum over Si, canceling out a factor of n. So this fluctuation, intensive fluctuation in the magnetization, can be given by a sum over those correlation, over the extent of those correlation functions, over the extent of that correlation function. If that function does not decay, indeed, we will find that that sum continues to increase over all values of j, and thus the fluctuations will continue to increase. And if the system exists in a thermodynamic limit, that sum will have an infinite number of terms, yielding an infinite size of fluctuations. So indeed, this Cij is a quantity that directly quantifies the correlations, the piece in mean field theory we must have been neglecting, and is clearly an important piece because it is a central quantity. It is what actually determines the singular behavior of the system near its critical point. So this function, this correlation function, has some characteristic length associated with it, and that characteristic length is what diverges. So indeed, the effect of correlations becomes bigger and bigger as we get near the critical temperature. We can plot that characteristic length. And at 0 temperature, it is 0. At high temperature, it is nearly 0. And at Tc, it diverges. So the importance of correlations become something we really can't neglect. And yet in mean field theory we have. And somehow we've still gotten some reflection of that symmetry breaking and associated collective behavior out of mean field theory. And somehow the fact that that correlation length diverges is not important at high dimension. Somehow the correlation between spins is washed out by the fluctuations of a single spin, which mean field theory can know something about. So we'll develop a way of thinking about these correlation lengths in the next lecture. I'm going to leave you with this today, and end on a little discussion about this critical exponent, new and something that we've essentially just discovered in this relationship. So the fact that I can write the fluctuations, which are of course proportional to the susceptibility. The susceptibility has a critical exponent gamma. This correlation function has within it a length that when I sum or integrate over that function, must know something about the critical exponent gamma that the susceptibility diverges with, but the exponent that determines the length scale over which that Cij, that correlation function, decays is different, is new. Turns out these are in fact not all unrelated. So there are lots of critical exponents. But there are only a couple which determine everything. So in fact, gamma is simply related to nu, the critical exponent that tells me how the correlation length diverges, through a numerical factor 2 plus another number, eta, which is known as the anomalous dimension. That tells you exactly how that correlation function diverges. What are the patterns that actually that function represents? If I know the nu and I know eta and I know the dimensionality of the system, I can compute beta. Beta turns out to be a numerical factor of 1/2 times d plus nu minus gamma. That's a simple thermodynamic consequence of the order parameter being simply related to the susceptibility through a derivative of the conjugate field. We've also introduced the critical exponent alpha as representing how the heat capacity diverges upon approaching the critical point. This turns out to be nothing but 2 minus nu times d. So in fact, there really are just 2 critical exponents that determine the entire universal behavior of the system near its critical point. How the correlation length diverges, and what the patterns look like at that critical temperature. This anomalous dimension eta. So in fact, if we were going to think about what the Ising model actually looks like, at different temperatures, so at T equals some low temperature, T1, the system is going to be largely in the all up or all down states. But there will be little defects that are formed, little islands of up in a sea of down. If I increase the temperature, it's possible to thermally excite slightly larger domains. Indeed, this correlation length is directly reflecting the characteristic size of those fluctuations. At very high temperature, the system is awash, equally likely to be up or down. But there will be regions that are locally enriched with spin up or spin down. The characteristic size of those regions as I cool the system down will grow. So let's say that this is some T3. Less than some T4, and this is some T4. At T is equal to Tc, if the correlation length diverges, that means that there is no characteristic scale for fluctuations in the system, which is another way of saying that all size domains are present. The system isn't stable in up or down. There's no sense of coexistence. There's no meaningful distinction between those two phases. So in fact, there's no reason for those fluctuations to be compact. Unlike at high or low temperature, where fluctuations will be expected to be compact. In fact, it's the ruggedness of those fluctuations, of the patterns that exist exactly at the critical point, which is what sets that anomalous dimension. How rugged those fluctuations look like is computable or is quantifiable from that anomalous dimension. Essentially how uncompact, how unspherical those fluctuations grow as I increase the size of the observation volume I'm looking over. So this is a sense for what we've missed in going to mean field theory, how we actually incorporate this physics into a correction that is manageable is something we'll consider in the next lecture. So stay tuned for that, and I'll look forward to seeing you all in the live session. on Tuesday. Okay.